If you're looking for a shortcut to, being genuinely well-informed, you are definitely in the right place. Today, we're diving deep into the tech stack behind instant, real-time communication. Think about Google Meet or even Discord in your browser, that moment you hit join. Our mission here is to really pull apart how we got past simple chat to these slick systems handling video, voice, and data. We're talking WebRTC, Flutter, Firebase, and even touching on AI and IoT hardware integration.
It's quite an architectural journey, actually, and it's worth remembering how tricky this used to be not that long ago, maybe less than 10 years. Building something where people could just instantly see and hear each other, that was serious heavy lifting. Months of work. You were dealing with custom servers, proprietary codecs, unreliable browser plugins. It was, frankly, a bit of a nightmare.
Right, so how did we leap from that mess to clicking a link and getting high-quality video almost instantly on pretty much any device? Where did the change come from?
The big game changer was an open standard, WebRTC, Web Real-Time Communication.
WebRTC. Okay, so what fundamental problems did that standard solve for developers? What did it take off their plate?
It's basically a huge abstraction layer. WebRTC allows browsers, phones, devices, whatever, to talk directly to each other, peer-to-peer or P2P. The key thing is WebRTC handles the really hard stuff automatically. Things like finding the best way to encode the video and audio, keeping it all synchronized, and crucially, it deals with NAT traversal. That's the headache of getting connections through home routers and corporate firewalls. Suddenly, developers didn't need to be deep networking gurus. They could focus on the app itself.
Okay, so it hides a lot of that network complexity. And you're saying that underneath it all, whether it's a simple chat or something way more complex, it boils down to just three core concepts, three pillars.
Exactly. Three fundamental pillars. The first one is all about capturing the world around the device. That's the media stream. This API gives your application access secure, permission-based access, of course, to the hardware, camera, microphone, even screen sharing. It gets the raw input.
I think I see. So when I mute my camera during a call, I'm not tearing down the whole connection and rebuilding it.
No, not at all. You're just interacting with that media stream. You find the right video track within the stream and basically flip its enabled switch to false. Simple toggle.
Makes sense. Okay, pillar one, media stream captures the input. What's number two?
Pillar two is the RTC peer connection. If the media stream is the sensor, the peer connection is the actual bridge. It's the secure, direct link between the two devices. It handles setting up that network path, managing the encryption, making sure the connection is stable and secure. It confirms the direct link works.
The bridge itself. Okay. And the third pillar, you mentioned this one might be a bit surprising.
Yeah, because WebRTC isn't just audio and video, which is what most people think. The third pillar is the RTC data channel.
Data channel. Okay, what does that let you do?
This is incredibly powerful. WebRTC gives you this secure, low-latency P2P pipe, right? The data channel lets you send pretty much anything through that same pipe. We're talking structured data like JSON packets, plain text, binary files, game state updates, control signals, anything, really. And because it uses the exact same underlying P2P infrastructure as the video, it's also encrypted and really fast.
Wow, okay. That data channel sounds like the secret sauce for making these apps truly interactive, not just passive viewing. But hang on, if the RTC peer connection is this direct bridge, how do two devices, just randomly out there on the internet find each other to even start building it?
That's the key detail. It's what we call the signaling gap. WebRTC itself, the standard, it doesn't define how peers discover each other or exchange that initial setup info. It only specifies how they talk after they've been introduced. So you need something external for that introduction. You need a signaling server.
A signaling server, so like a digital matchmaker, or maybe a phone operator who connects the call but doesn't listen in.
That's a great analogy, the phone operator. It just facilitates the initial handshake. So walk us through that handshake. You said 6 steps.
Yeah, the connection lifecycle. How does it actually unfold?
Okay, so first, both sides get their local media ready, local media setup, and create their own RTC peer connection object. Then the person initiating the call creates what's called an offer. This offer basically describes what they can do, codecs they support, things like that. The other side gets the offer, looks at it, and generates an answer. This offer-answer exchange uses a specific format called SDP, Session Description Protocol. Think of SDP as a technical contract for the call.
Okay, so they've agreed on the terms of the call. The contract is signed via SDP. Now they need directions to actually, meet up on the network highway.
Yeah, exactly. That brings us to the ICE candidate exchange. ICE stands for Interactive Connectivity Establishment. It's bit of a mouthful. Basically, each device figures out all the possible ways it might be reachable on the network, its local IP address, its public IP address after NAT, maybe even a relay address. These are the IC candidates. They swap these candidates, these sort of network GPS coordinates, through that signaling server we mentioned. Once they find a path that works for both of them, bam, the direct P2P connection is established.
And then live communication starts. Wow. That's quite a delicate dance happening behind the scenes, all handled automatically. Okay, let's shift gears to actually building this in the real world.
Yeah.
In a modern production setting, Flutter often comes up. Why Flutter for these kinds of real-time apps?
Well, the big draw is writing code once and having it run pretty much everywhere. Mobile, web, desktop, even embedded systems sometimes. Flutter lets you have one code base for all these platforms. And critically, for video, which needs good performance, the Flutter WebRTC plugins handle the rendering efficiently while still giving you that cross-platform consistency. Code reuse plus performance.
Makes sense. And we talked about needing that signaling server for the handshake. You often see Firebase, specifically Firestore, used here.
Mhm.
Can you clarify Firestore's role? What exactly does it do? And maybe more importantly, what doesn't it do?
Firestore works really well because it's a real-time database. Changes update almost instantly for anyone listening, so it's perfect for that quick back-and-forth signaling. It acts purely as that lightweight phone operator. Peer A writes its SDP offer and its IC candidates to a specific place in Firestore. Peer B is listening to that spot, grabs the info, and writes its answer back. It's just for coordination. The critical point is the actual audio and video, the heavy stuff. It never goes through Firebase. Once that P2P link is up, Firebase has done its job for that connection.
Right. Keeping the media P2P is key for latency and privacy. But networks can be messy, right? My connection might be fine. But what if the person I'm calling is behind a strict corporate firewall or some complex home network setup? That direct P2P connection might just fail. Stun helps find the public IP, but
Yeah, stun alone isn't always enough. P2P connections fail more often than you'd think, especially in trickier network environments. That's where you absolutely need a fallback.
and that fallback is.
It's called traversal, using relays around NAT. While stun helps peers try to find a direct path, turn servers act as a relay, a middleman. If a direct connection just isn't possible because of firewalls or whatever, the traffic flows through the turn server instead. Each peer connects to the turn server, and the server relays the media between them.
Got it. So turn is like the connection insurance. It might add a tiny bit of latency, maybe cost a bit to run the servers, but it guarantees the call connects, which is vital for anything professional.
Absolutely. In production, reliability is king. You need turn servers. And speaking of production concerns, security is obviously huge, especially with video and audio flying around.
What's the core security guarantee here? How can developers reassure users?
Security is really baked into WebRTC from the ground up. It's not an afterthought. All WebRTC traffic audio, video, and the data channel is mandatorily encrypted. It uses strong standard protocols, DTLS for setting up the secure channel, and SRTP for encrypting the actual media streams. Plus, before any of that even happens, the browser or operating system itself won't let an app access the camera or microphone without explicit user permission. So the input is locked down too.
Okay, secure by default. Now, thinking about making the app feel polished, production ready, users expect things like instantly muting their mic or camera. How do good apps handle these dynamic controls smoothly?
Yeah, user experience is crucial. The key insight is you don't need to renegotiate the whole connection for simple things like muting. Instead of tearing anything down, the app just targets the specific media track, the audio track from the mic, or the video track from the camera, and changes its enabled state. Set enabled to false, it's muted instantly. Same for switching cameras on a phone. The switch camera function just tells the existing video track to use a different source. It's seamless, no connection drop.
And network glitches happen. We've all seen that reconnecting message. How does the app know when the connection's getting unstable to show that kind of feedback?
The RTC Pure Connection object is constantly providing status updates. It has states like connecting, connected, disconnected, failed. Your application code listens for these state changes. If it suddenly gets a disconnected state, it knows the connection is temporarily lost but might recover. That's the trigger to show reconnecting to the user. It keeps them informed.
Super important. Okay, let's face the big challenge. Scaling. This peer-to-peer model, this mesh architecture where everyone connects to everyone. It sounds great for small calls, maybe 2 or 3 people, but it must fall apart pretty quickly with more participants, right?
No, completely. It hits a hard limit fast. The problem is complexity and bandwidth explode quadratically. That's ONN. Think about it. With 4 people, each person sends out 3 streams and receives 3. That's manageable, maybe.